Okay, so one of the most common use substitutions will involve quantities for which the integrand is raised to a power, like we had been saying before, like, we had sine of x, let's say, squared. And for that, we actually get a nice rule that we had before with the same name, but now for integration, which is the general power rule. So I'll just give you the rule first, and then we'll see some examples. So this is the so-called general power rule for integration. We saw the power rule earlier for things like the antiderivative of x dx. That was x to the p plus 1 divided by p plus 1. So now we're going to see the general case for this rule. So if g is a function, a differential function, I should say, a differential function of x, then the antiderivative of g of x to the power n times g prime of x dx. Notice that the antiderivative is present there. Is equal to g of x to the n plus 1 divided by n plus 1 plus c. So long as n is not equal to minus 1, because if n is equal to minus 1, then we have 0 in the denominator, and we cannot divide by 0. So notice that this is very similar to the rule the power rule that we had before. And this is equal to, so equivalently, if we use a substitution u equals g of x, then that means that we have u to the n du is equal to u to the n plus 1 divided by n plus 1. There's an n, that's a u, plus c. And again, so long as n is not equal to minus 1. Okay, so let's see some examples of this. It's a pretty neat rule. So we have 3, let's say we have the antiderivative of 3 times 3x minus 1 to the power 4 dx. Well, based off of our rule, what do we need? We need a function g raised to a power and its derivative. Do we have that? Well, we have a function g raised to a power, and the derivative of 3x minus 1 is 3. So yeah, we do have that. So by our rule, that is equal to u to the n plus 1. So let that be u, and that means that we have 3x minus 1 to the 4 plus 1, so that's 5 divided by 5 plus c. So again, this and this will form our du, and this right here forms our u. So another one. What about if now you go to 14th Street and somebody gives you the antiderivative of e plus 1 times e to the x plus x dx? This one may look a little bit more complicated, but again, it's just a matter of noticing patterns. What is the derivative of e to the x plus 1? The derivative of e to the x plus 1 is just e to the x. So let me call f of x e to the x plus 1. This is one technique that you can use. And the derivative of that is just e to the x. So notice that there's no e to the x by itself. So this is not the u that I need to use. If I let the other parentheses, the other expression, be g, then I have e to the x plus x. The derivative of this is e to the x plus 1. And guess what? That appears up here. So I know that g is going to be my u. So this is one way of quickly noticing the pattern here if you are not too familiar with this. So now that I have a pattern, what do I need to do? Well, again, by the general power rule, I have a u. I raise that u to the n plus 1 and divide by n plus 1. plus c. What is the exponent here? The exponent here is 1. So I have e to the x plus x. I'm using the substitution of u equals e to the x plus x here. So I have e to the x plus x to the power 2 divided by 2 plus c, because I'm letting this piece be u. And this is the derivative of u, or u prime. So this right here is my solution. So another one. What if we had 3x squared times the square root of x cubed minus 2 dx? Well, similarly, notice that the derivative here of x cubed minus 2 is here. The derivative of x cubed minus 2 is 3x squared, so we know that our theorem applies. But now notice that this is raised to the power 1/2, so we have to be a little bit more careful here. So this is what we originally have is, let me do the substitution actually, let's just do the substitution. U is equal to x cubed minus 2, so that means that du is 3x squared dx, which is exactly what I have. So this is the integral of u to the power 1/2 du, which is equal to, by our rule, u to the 1/2 plus 1 divided by 1/2 plus 1 plus c, which is equal to u to the 3 over 2 times 2 over 3 when we do it, plus c. And u was x cubed, so let's bring it in. So this is x cubed minus 2 to the 3/2 over 3. So using substitution, we use the guidelines from the previous video to solve this, and we use the theorem from this video, from this lecture, to solve this. Okay, I use this rule now. I did the substitution, and then I solve the antiderivative using the rule, the general power rule. Okay, let's do one more, maybe two more. Let's see. What if now somebody comes up to you and gives you this, negative 4x divided by 1 minus 2x squared to the power 2 dx? Well, we haven't really dealt much with these before. Whenever you have something like this, it is often useful to rewrite them using the negative exponent. So meaning bring the denominator to the top. So this is negative 4x times 1 minus 2x squared to the power minus 2. When we bring this to the top, the power becomes a negative. Now, here clearly we can see that the derivative of this piece of negative 2x, 1 minus 2x to the 2 is equal to negative 4x. So our general power rule will apply. So this is going to be equal to 1 minus 2x squared minus 2 plus 1 divided by minus 2 plus 1 by our general power rule, plus c. So this is equal to 1 minus 2x squared minus 1 divided by minus 1 plus c, which means that our solution is negative 1 divided by 1 minus 2x squared plus c. When you bring down the expression to the bottom, and this negative 1 just makes everything a negative. So this will be our solution. And notice how quickly I'm solving these problems using this rule. Once you have identified what the inner function should be, then it's just a matter of applying the theorem. Let's do one more, 5. So number 5 says the following. Let's say you're given the integral, say you go to Chambers Street, you're given the integral of cosine squared x times sine of x dx. Well, here we have to be a little bit careful. So notice here that the derivative of cosine is negative sine. And why am I talking about cosine and not sine? Well, cosine is raised to a power 2. So clearly f of x here, the outer function, is x squared. So I want to make sure that I use the inner function as g of x to be cosine of x. But the derivative of cosine of x is negative sine of x. But negative sine of x is not anywhere in this problem. But luckily for us, a negative is just a constant, it's just minus 1. So we could actually introduce negative sign in here. How do we do that? Well, like this. I'll take our integral, and then I'll say, okay, this is the same thing as cosine square of x times -1 times negative sine of x dx. Notice that when you multiply -1 times negative sine, you're going to get plus sine again. So this definitely works, and this is using the constant multiple rule. I'm going to pull out the -1, so it's going to be negative the integral of cosine square x times negative sine of x dx. But now notice again that I can use now the general power rule, because I have u to a power, I have u to the power 2, and I have its derivative right here. This is the u, this is u, so I could use the general power rule. So this is minus, because of the negative, cosine of x to the power 2 plus 1 divided by 2 plus 1 by the rule, plus c. So it's equal to negative cosine of x cubed divided by 3 plus c. And that is our solution. Okay? Now, for some integrals, this rule is not going to work. It will work for most integrals, but for some of them, it's not going to work. So, note, this rule may fail. Okay, it may fail. So consider the following. I'll leave this as an exercise. This is somebody gives you the integral of x times x squared plus 1 squared dx. Here we have a problem. The problem is that if you let g of x be x squared plus 1, then g prime of x is equal to 2x dx. But the issue here is that I only have, actually this one is going to work. What I meant to do was remove this x here. If you remove the x here, if you remove the x here, this is not going to work because we don't have an x here. So for this particular antiderivative, what you should do is just expand it, meaning do x squared plus 1 times x squared plus 1 dx, because the general power rule is not going to work because we are missing this antiderivative. And then you could find the integral of this. So it's going to be x to the 4 plus 2x squared plus 1 dx when you expand this. And then if you find the antiderivative of this, it's going to be x to the 5 over 5 plus 2x cubed over 3 plus x plus c. Okay, so the general power rule may fail. That's the important piece here. It may fail if the derivative of a function is not in part of the integral of the integrand. Okay? In the next part of this lecture, we're going to be talking about how to actually use the change of variable rule with the definite integral. Everything that we've done so far has involved the indefinite integral, but things will be interesting when we use the definite integral, especially when it comes to the limits of integration.